Okay, I've had a couple questions about the thermochemistry enthalpy recap assignment, and I wanted to hopefully answer or clarify a couple of those old concepts. I'm going to go through a couple problems that we already did in this class last time we did thermochemistry, but point out some of the details for that assignment that you want to be aware of, and I hope this helps. If you still have questions after this, feel free to email me and I can answer those. But your calorimetry problems, your first couple problems are calorimetry problems. Your key concept here is the chemical reaction that's occurring. Sometimes it occurs in a little container like this. It's not actually participating in the solution. So it just has heat that gets distributed out into solution. But sometimes you put a solid in water and it dissolves. So it could be either one of those. But you want to know how much heat does the water absorb. And that's going to be calculated by your Q equation. C for water times the mass of water times the temperature change for the water. And for some AP problems, you might have the C value be something other than the 4.184, which is your joules per gram degree Celsius for water, your specific heat capacity of water, and the problem would give that to you specifically. The mass is going to be the mass of just the water. If you have a solid that gets dissolved in water, you need to include the mass of the solid that gets dissolved in water. So maybe I have 12 grams of sodium chloride and I dissolve it in 100 milliliters of water. Well, 100 milliliters is 100 grams, and so the total mass I would put in for this mass M here would be 100 plus my 12, and I do 112. And it actually does change your specific heat capacity a little bit, and a problem might specify that, it might not, and if it doesn't, you just use 4.184 in the mass of your combined. If it's put into a combustion container like this, you will not have to add any mass into the mass of your solution. So what do we do with this number? This will give us joules. And it'll be joules either absorbed or released by our chemical reaction. Either the water heats up or cools off. These joules will then go over and we'll compare that to the amount that we reacted or dissolved or whatever our process is. And that's how we get our delta H. The enthalpy change for the process is going to be the Q for the process divided by our number of moles in the process that actually reacted. So the Q, usually this is given to you, or they'll want you to get this in kilojoules, so we'll do conversion between joules and kilojoules over here. And then you just need to identify what are the moles that actually react in my vessel. Actual moles reacted. And you divide those out and you'll get your enthalpy change for the process. So let's look at that. This is an old problem from one of our assignments or our notes earlier in the class. Calculate the molar heat of, this means the heat for 1 mole, and you have a couple questions that ask that. How much energy is released for 1 mole of whatever is happening? In this case, we're dissolving calcium chloride in solution, and it says 14.5 grams of calcium chloride dissolved in 500 milliliters of water. And this is our work that we had. This problem should be in your notes a while ago, but I'll walk you through it again here. The 500 milliliters of water absorbs our energy here, and you can see we start out at 23 degrees Celsius and we go to 28. That means we have an exothermic process here. When it dissolves, it releases heat, and we want to know how much heat gets released. That's going to be our energy absorbed or released. We'll convert that into kilojoules, and then we want to divide that by the number of moles of calcium chloride that reacted in our process. In this process, it just dissolved, so we'll convert this to moles. Divide those out, and you'll get how many kilojoules 1 mole of calcium chloride dissolving will release. The only thing that I really want to point out here, when you do your Q for a solution, how much energy the solution absorbs, we assume that our specific heat capacity is the same as water. But the thing I want to point out, this is not 500. Why is it not 500 grams? Well, in this process, we dissolved a compound, so there's 14.5 grams added to the solution, and that 14.5 grams has to also heat up. If it was done as a reaction in a little container like this, where it didn't participate, we would not add that mass, but in this case, we do have to add that mass because it actually gets dissolved in that solution. So that would calculate our total energy that the solution absorbed, and that total energy would then be converted to kilojoules. Our grams of calcium chloride converted to moles, and we take our kilojoules divided by our moles, and we get the molar heat of a solution for this particular problem. You have a couple problems like that. I want to just go over these problems on your assignment real quick and just point out a couple things. Number one is probably your hardest one. The calorimetry experiment here, it gives you two amounts. It gives you the mass of magnesium and it gives you a volume and a molarity of HCl. So you want to use this chemical reaction. We react these two together and produce magnesium chloride and H2 gas. And you'll want to balance this equation. I'll balance it for you, two of these guys, and that's it, we're balanced. We want to know how much energy gets released by this reaction. And to do that, our temperature change of our water is just going to be these two values. And we'll plug that into our equation, Q equals C times M times delta T. You don't need to be concerned about adding this mass in. The reason you don't need to is 200 milliliters is 200 grams and 0.1277 is not a large change for that. You can if you want to. You could do 200.1277. Use the specific heat capacity of water, and then my temperature change would be the difference between these two, and I can calculate how much energy the water absorbs. That would be converted into kilojoules, and then to get my delta H for my reaction, I want to know how many kilojoules for however many moles reacted. Well, this part right here, you have to do a limiting reactants problem and figure out which one of these ran out. One of these is going to be left over, and whichever one ran out is the one that actually reacted, and that's the number of moles you'll want to divide by to get kilojoules per mole. That'll give you kilojoules per mole of either magnesium or kilojoules per mole of HCl. It says calculate delta H for this reaction as it's performed. That'll be just your energy that gets released from this chemical reaction as it's performed. And then the delta H per mole of HCl. So delta H per mole of HCl, you'll want to take kilojoules per mole of HCl. If HCl is your limiting reactant, you'll have your answer right away. Just kilojoules per mole of HCl. If it's not your limiting reactant and magnesium is your limiting reactant, then you're going to have to figure out, well, for every 1 mole of magnesium, I have 2 moles of HCl, so this would be, you would have calculated delta H for the reaction. Let's just, let me just show you that. If magnesium is a limiting reactant, and I do kilojoules per mole, my kilojoules from this equation, per mole of magnesium, let's say I get 100, it's not this, but 100 kilojoules per mole of magnesium. Well, that's going to be 100 kilojoules per mole for this reaction, because the reaction is written to have only 1 mole of magnesium in it. It'd be released, so this would be negative value, we'd have a negative value here. How do I get per mole of HCl? Well, for this reaction, I'd have to divide the reaction by 2 to get 1 mole of HCl. And if you divide a reaction by 2, you have to divide the energy that produces by 2. And for the answer for this problem, I would have to say negative 50 kilojoules per mole of HCl. That's going to be a different number than it is per mole of magnesium. Don't write this answer down. This is not your answer, but that's the process here. So identify what limiting reactant is. If the limiting reactant is HCl, then you're done because you'll get how many kilojoules per mole of HCl. If it's not HCl, you need to consider this 1:2 ratio just like we did here to get per mole of HCl. Your other problems, number 2 and number 3, are just like that. But this one you're dissolving or putting cesium in water. You would not include this mass in your Q calculation because the Q, we're keeping that mass separate, and we know we're keeping it separate because it's in a sealed glass vial and just energy is transferred there. So don't include the mass of cesium there, just the mass of water. And your last one, we're dissolving ammonium nitrate, and if you're dissolving it, you do need to include the 8 grams in your 1 liter of water, and 1 liter is 1,000 grams. So include that 8 grams in that calculation. The other ways that you can calculate enthalpy that are on that sheet, you have a couple problems with standard enthalpies of formation, some of the products minus some of the reactants. Just plug in your values in the problem. These are just plug and chug problems. So this is an example that you guys had in your notes earlier. And if this was our heats of formation, we just sum our products. Just a reminder, you have to multiply these by the coefficient that's in front of them because the delta H formation is just for 1 mole of that particular compound. So here we'd multiply by 2 and multiply by 3 for our products, and same thing for our reactants. Some of the products minus some of the reactants gives you your delta H for your reaction. You might have some problems where they give you this value. One of these is an unknown, and you have to work backwards. So you'd set up this equation, and you'd have your x value somewhere over here to solve for, and you'd know the right side of the equation. Okay. Hess's law problems, quick refresher for these. If I want to know the equation up above, I have all the equations below and their delta H values. I just do this. I want to identify how can I add these equations together to get the equation above. And the C, the carbon, I identify is it on the correct side. It is on the correct side. I want it on the reactant side, and I want 2 of them, so I'm going to multiply this whole reaction by 2. And that means my delta H over here will get multiplied by 2. I find H2. H2 is right here. It's on the correct side, it's on the reactant side, and there's only 1, and I only want 1, so I won't do anything to this bottom equation. My top equation here, my C2H2 is what I'm looking for, and I find it's on the wrong side, so this equation is going to have to be flipped over. If you flip your equation, you multiply this by a -1. It changes the sign of it. So I'm going to double this, multiply this by a -1, and add those equations together. And if you do that, I'll flip them over. Here it is, I flipped this over. Now it's on the correct side. My carbons are on the correct side and the correct number now, and my H2 is on the correct side and the correct number. I can add these equations together. When I flip this, the sign changed. When I doubled this, I doubled the value. And then we just want to check to make sure all of these add up to the equation above. Cancel everything that can cancel. H2O liquid cancels. O2, 1/2 O2 plus 2 O2s, 2.5 O2s. 5 halves is 2.5 O2s. And the only thing that's left is our CO2s cancel as well. The only thing that's left is carbon, hydrogen, and C2H2. You might hear my daughter screaming in the background there. So these add up to our equation that we want above. And these values, if you add them up, will give you your delta H for your reaction that we care about. And these come out to 226.7 kilojoules per mole. And that's what we'd report for our answer right up here. And that's how you do Hess's law. You also have problems with bond energies. Bond energies, quick refresher. It takes energy to break a bond. And when a bond is formed, it gives energy. And so when you're solving for your delta H for bonds, you want to do the sum of the bonds broken. That's going to be your reactant side. So this one's a little bit backwards. It's not the same as our products minus reactants, because the bonds on the reactant side are the bonds that get broken, and the bonds on the product side are the ones that get formed. And why do we do it reactants minus products? Well, we want, if there's energy released, and bonds forming is how we release energy, so this would be released energy on this side. If energy is released from the reaction, we want exothermic. And exothermic means that our delta H needs to be less than 0. And if we have more energy released than energy absorbed, to get a delta H less than 0, we have to do reactants minus our released energy, and we get a negative delta H. So a problem would look like this, maybe a very simple problem. We have to break both of these bonds, and we're going to make both of these bonds. And we would look at a table of values and figure out how much energy does it take to break an H bond. Well, it takes 436.4 kilojoules for every mole that breaks. And our fluorine bond, 156. So this would be the energy invested. And this would be the energy that we get out of it. 568.2. We form 2 of these bonds, so we multiply by 2, and we get this number over here. And that's how much energy is released. And in this particular problem, what do we have? Do we have more energy invested or more energy released? And the answer is we have more released energy. So this would be an exothermic reaction. We should get a negative delta H. And if we do energy, the sum of the energies to break bonds minus the sum of the energies to form bonds, we do get our negative value there. So there's a quick refresher for those concepts. I hope that helps for some of you who are kind of reeling and trying to figure out this old material. If you have other questions, feel free to ask, and I'd be glad to answer them.